Right. So, we were discussing the vibrational spectroscopy, and we started introducing Raman spectroscopy in vibrational spectroscopy. So, in today's lecture, I will try to cover mostly vibrational spectroscopy, some theoretical aspect and lots of application of FTIR as well as Raman spectroscopy in daily life, in bio, in analytical science, in medical science, where we can use the FTIR and Raman for characterization, analysis and all those. Right. So, let us start with some recap. So, fundamental principle is exciting the vibrational level, that is what happens, and we also discussed that in any of the measurement it follows the Beer-Lambert law, A equal to ECL. Only difference is, rather than the electronic state, we are talking about the vibrational state of the right. So, yeah, so I was just discussing, in any spectroscopy selection should are followed, the absorption happening, the particle are excited from the ground state to excited state. The only difference that here we are using the IR light because the energy gap is low, right, and it is a bond vibration. So, it follows the Hooke's law that we have already discussed, and then you have the generally the y axis is like a arbitrary unit, x axis is denoted as a wave number Cm inverse, that is what is the happens. And mechanism, like in IR beam, again variable path length, anti interference happens, and then you detect signal to noise. So, because of the this is less, so signal to noise averaging you have to do little more, that is what we have discussed. And then we were trying to discuss the Raman. So, Raman spectroscopy is a type of vibrational spectroscopy. It is a most of like IR and Raman both absorbs in the vibrational range or IR range, and it is actually assess the fingerprint of the molecule because each of this bond has a definite vibration, that is what we have discussed. It is based on inelastic scattering of a monochromatic excitation source. What it means that when the light is shined on the molecule, most of the light goes in elastic scattering, some very few goes for inelastic scattering, and that excites the vibrational level in the molecule, and that is what we are trying to observe here. So, routine range the range that we observe is 200 to 4000 centimeter inverse. The selections rule are complementary to IR. So, whatever mostly like a CO2, the centrosymmetric molecule, it is a one of these symmetric stretching is IR inactive, but it is Raman active. So, selection rule dictates which molecular vibration are probed, and some vibrational modes are IR active, some are Raman active, and some are both active, right. So, that is the thing, it is not a mutually exclusive कि IR होगा Raman नहीं होगा. In some case it is true, but most of the case both IR active and Raman active, right. The great part of Raman spectroscopy that you do not have to do much sample preparation, right. IR water was observing huge and that was a problem, but here it is an inelastic scattering giving exciting the vibration level. So, you do not have to worry about water, let it be water, we will do the experiment in water. So, liquid, solid, gas, whatever you see, whatever you have, you can use the Raman spectroscopy for detecting it, and it is compatible with wet sample because water is not a problem, you do not have to do anything else, it is a ambient temperature. The only thing that I had discussed with this because of the inelastic scattering. So, that is a these are electronic state that we have already studied. UV visible goes to higher electronic state, fluorescence comes back from there. IR, because of this inelastic scattering, it like if you look at in the left hand side, it excites some of those vibrational states, and that is what gives you. So, what is there, so most of the molecules, say excitation is done by this 1,000,000 photons that is doing inelastic scattering, that excites the vibrational levels, and that gives you the Raman spectrum, right. So, IR absorption happens. In IR, it is absorption that is giving the spectrum. In Raman, it is a scattering that is giving the spectrum, right. And the only issue is that here 1 in 1,000,000 or something, we are absorbing the photons which is giving the Raman spectrum, right. So, what Raman is basically, if you look at this Raman, it is giving you or exciting to some imaginary vibrational state to you, right, and it happening because of a scattering. So, it goes, excites it, and it comes back. So, something is shifted, right. So, if you look at Raman, some shifts, it is a Stokes shift, and in other, like if you mu plus mu emit, that is a delta shift that you get, is either Stokes shift or anti-Stokes shift. So, here is excitation, usse idhar hoga to Stokes, right, on higher frequency it is anti-Stokes shift. So, that is what it gives you in the Raman spectrum, right. So, the other thing that people have done it, I will not go into that much detail, it is called resonance Raman spectrum. So, resonance Raman basically goes to higher excited state and it comes back, essentially to enhance the sensitivity, but I do not want to go too much detail. The good part of Raman, since it based on a scattering principle, so you do not require a particular wavelength for doing Raman, right. You can use any laser light to excite the higher vibrational state. So, Raman can be done with any laser light. Why laser light? You require an intense light source to excite it. Why intense? Photon count has to be high, right, lux has to be high, because we are based on low probability, 1 in, that is what is happening, right. So, if you are doing say near IR 785 laser, you see 2 low probable peaks, that is one for Stokes, delta, whatever the frequency minus delta mu and plus delta mu, it is a anti-Stokes shift. Similarly, if I am doing with green laser, we see a peak there, right. So, Stokes and anti-Stokes shift. So, these are basically Raman spectrum that we get, right. Now, this is little bit of concept that we were trying to discuss. For molecule with a center of symmetry, it is not IR active, but Raman active, and vice versa. This is called symmetrical molecule, like CO2 we have seen, both symmetric stretching, it is a IR inactive, Raman active, right. So, that is a centrosymmetric rule. And for a small molecule, basically for any of the small molecule that we are talking, IR and Raman complement each other. Some modes are not IR active, some modes are Raman. So, where you should use IR, where you should do Raman? So, typically you can use both, right. If your lab is fancy, both the instrument, I would love to do both, because some are not IR active, some are not Raman active. So, you can use both. The only issue is Raman is expensive than typical IR. So, for like if you want to working on a say diatomic homonuclear molecule like N2 or O2, it has a dipole moment, right. So, so there is no gain by vibration, so no IR spectrum, but like say N2 equally stretched, right. But Raman does not have any requirement, so you can use Raman for those cases. In Raman, actually you have to have some polarizability changes, that is enough. So, nuclear motion rather than a permanent dipole is required. So, just polarizability is good enough for molecule to show the Raman spectrum, right. So, that is what. So, if you take any small molecule, here I am giving an example, say like say this molecule, here we have a IR infrared and Raman for crystalline cysteine, right. You are asking about cysteine. So, cysteine is a crystalline form, and you can see we are getting all the many modes in IR and Raman. So, like you can look at this structure, it is a COOH, CHNH2, CH2, SS. So, it is a 216 cysteine bond has formed, and now this is IR spectrum, this is Raman spectrum. When you see the huge signal at 3200, it is a OH stretching you are getting because of COOH, but that is not so intense. So, Raman spectrum looks much simpler, baseline is quite flat, and many of the peaks are just complementary to each other, right. So, that is a good part of that. So, NH3 deformation and carboxylate antisymmetric vibration you have around 1600, that typically we know that is coming from ketonic group, CO group, typically for amino acid and all those. So, that is excellent part of that. Now, here the oleic acid and methyl ester, that is a structure of the molecule. Now, you look at the FTIR versus Raman. So, what concept I think all of you are clear. Here is my sample, IR goes, it absorbs. In Raman it goes, scatters, and that scattering you can see it. One is elastic, जो सेम ही फ्रीक्वेंसी पर हो, और एक एंटी स्टॉक्स, एक स्टॉक्स जो different frequency पर आता है. So, that is what you see. Now, in Raman CO peak clearly can be seen, C double bond can be seen, and many other peaks that you can, CH peaks and all those you can find it out. So, mostly it looks quite complementary for FTIR and Raman, right. So, that is another example that we have. The good part that both of this, now another molecule let us look at, mylestine and indane. You see so many interesting peaks are coming, and more or less they are matching very well with each other, right. We are just on top of each other. So, for large molecule IR and Raman, effects essentially the same set of spectrum. Raman spectrum shows conformation dependent shift and splitting, and Raman spectrum is also shows that what we have discussed, hypochromic shift. The good part that both of them shows the fingerprint. That means, one kind of functional group mostly come there with little variation. So, you can identify which kind of functional group is reporting at what frequency, OH, NH, NH2, CH, C double bond O, CON, whatever it is. So, it is a quite nicely overlapping, and therefore, you can find a table of this that we have earlier seen it. So, assignments based on the vibrational spectroscopy, alkane, alkyne, alkene, CH, CH2, like whatever, OH, NH, all those you can find in a table, and these are the typical range of the each functional group that is there, and this helps in identification of the molecule that is under investigation. So, if you are again, this is the same table that one can have it, Raman spectrum for chemical analysis, you can find in a book. So, why this is important for a chemist? I already told, chemist people keep synthesizing molecules, many steps molecule, and once they synthesize they have to characterize what they have synthesized, because these are like a step reactions, step 1 से 2 पर, 2 से 3 पर, 3 से 4 पर. अगर 3 ही नहीं सही बना है तो 7 पर कैसे जा सकते हैं. Many steps they have to do characterization, and they do it each of the step that they conform it, right. And Raman or FTIR plays an important role in such characterization, because they identify if they wanted to make the ether, it has not produced ester, right. So, that is identification one can do it. You can, there are many techniques, one of them is FTIR, Raman, mass, NMR, they have to do all those, and that helps in identification of the. So, now both are complementary. Do you see any advantage of Raman over FTIR? Do you have any advantage? One thing I told you, it requires laser light, so cost to बढ़ गया, right? But what else? How it is better? Can you find it out some? So, first and most important for, say if you are a biological chemist, your whole life evolves or revolves around a biomolecule. Biomolecule don't like to be in other solvent, they are more than happy in water. IR is saying I am not very comfortable with water, and you don't want to put your biomolecule in benzene, right? So what option I have? I will do pranam to IR and say Raman is waiting for me, I will go to Raman, right. So it's a water can be used as a solvent for Raman. It's extremely suitable for biological sample in the native state, because water can be used as a solvent. So just you put your biomolecule in capillary in water and do Raman, you don't have to worry. Now although Raman spectra arises from molecular vibration at IR frequency, the spectrum can be used using visible light or NIR. So it's independent of what radiation source you are using, right. Any radiation source you want, you can use for Raman. It does not matter whatever you are using. The glass, quartz lens, cell, optical fiber can be used, standard detectors can be used, you don't require any fancy things. The only like for some overtain and combination bed, few spectral overlap we have. If you look at the spectra that I was discussing, Raman shows relatively much beautiful and sharper spectrum than FTIR, right. So Raman intensity also somehow depends upon the concentration, because if you have more molecule, more scattering and more intensity, you get it. That's, so you remember where was the first Raman spectra observed by C.V. Raman? In a neat benzene, माने केवल वही था. So concentration plays an important role in Raman, and you can use any laser power, right. The only problem, if you look at all of these guys wants to excite electron, Raman, FTIR, UV visible fluorescence. So sometimes you encounter that you are overshadowed by fluorescence light, right. So basically this is coping up with or without fluorescence, you have a problem. So if you don't bleach it properly, bleach माने fluorescence को अगर नहीं साफ करेंगे तो कोई पीक ही नहीं दिखता है. So basically you have to photo bleach with long exposure of laser radiation, so that fluorescence is not coming, and then like even in the broader spectrum you can get the Raman spectrum. So after 2 hours of photo bleaching, in the same broad overlap where nothing was seen, the beautiful spectra emerge from the Raman. So you have to be careful when you do Raman. Many times it can be happen that your Raman spectra is shadowed by the fluorescence that is coming, right. So those are some of the critical observation that one has to take care of. Then it's a vibrational spectrum, right. So Raman is a vibrational spectrum. So essentially you have to have UV visible near IR radiation source with a laser, and in between you have a sample cell where you are getting the Rayleigh scattering, Rayleigh radiation, the elastic one, and then you have inelastic one, which excites basically the virtual state, and you get scattered photon, Stokes shift at lower frequency, anti Stokes shift, right. ऐसे जाएगा स्कैटर होकर कुछ ज़्यादा फ्रीक्वेंसी पर कुछ कम फ्रीक्वेंसी पर आएगा, दैट्स ए Stokes and anti Stokes shift, and that's what is there. So now all fantastic. In real life can we use these guys? Fantastic theory, good instrument, and biological application I already showed you. Let's talk about some application. These 3 girls are sitting in front of me, right. What basically female like? सजना सवरना सबको पसंद है ना, उस पर बहुत पैसा खर्च करते हैं, राइट. एंड कुछ गले में अगर नेकलेस हो तो उसमें क्या हर्ज है, isn't there or not? So what is the favorite necklace that you use? सबसे सुंदर नेकलेस किस चीज़ का होता है? डायमंड होता है, गोल्ड होता है, और तीसरा प्लेटिनम भी होता है, सिल्वर, पर्ल. Okay, so pearl, like you know, the for identification of pearl, right, if you go to a shop and this guy says, madam ये तो असली मोतियों की माला है, ले लो, and they charge you 6,000 rupees. So you have 2 options. Option 1, trust on him, and pay him. और घर आके पता चले तो नकली मोतियों की माला है कुछ दिन में it's getting, then you feel disheartened. Is there any way that you can find which is the authentic versus non-authentic? Have any of you have purchased, right? Pearl, you know how pearl is cultivated? सीप में, तो सीप समुद्र में रहते हैं, right? And they take time to cultivate it. Have to be on sea is getting polluted, बेचारे सीप जिंदा कैसे रहेंगे कि मोती बनेगा, right? That's another issue. But basically this is cultivated, and but you know the fraudulent guys are also there. They will make some pearl and sell you. So you know what is the constituent of this? Very good, calcium carbonate. Now you have as a science student, you know where it is cultivated. Biology guys knows. You know chemistry, what is the constituent. Can you use any of these spectroscopy that I taught you? Now I don't want to make a solution of this, right? And I said Raman can be used in liquid, solid, gas. So let's use Raman to find it out. ये मोतियों के माला में सच्चाई है या it's just fraudulent, right? You record a spectrum. So calcium carbonate, that's what she said. She will take this one bead of pearl and put under Raman, and you find that calcium carbonate giving you 3-4 peaks, pearl is also giving 3-4 peaks, and then fox pearl, so many peaks. As soon as you get this spectrum, 10,000 रुपया बच गया, right? You know that this is a fraudulent pearl, right? So that's the one of the your daily life application of Raman spectrum in jewelry shop, right? You can now get in a bigger कौन सा Jhaveri something, no? You can propose them, just buy a Raman spectrometer, all the fraudulence can be caught immediately. That's the application of one of the application of Raman in your day-to-day life. I will come to other application as well in biological and medical science, but since these three girls were sitting, I thought let's start with that. Okay, so today what we discussed mostly the basic concepts of Raman, the where you can how it is different than IR. The principle is different, you require a laser light, it is a concentration dependent, and it is quite complementary to IR for many of the analysis. We will stop it here and then we will continue. Thank you.